So we ended here for the net ionic equation. So these were all the answers. So I'm just, if you have any questions, I'm going to go over the answers. If not, let's just keep moving on. Hopefully you've already grabbed a calculator because it's going to be a good amount of math today. Any questions on these net ionic equations at all? No? Okay, I'm going to move on. So, part of that question, we remember we did this. We did one of these practice free response questions last time, and we did part E. Now we're going to do part C. So it says identify a pair of the solutions that would produce a precipitate. That means solid when mixed together. So if the first things first is that we're going to the prescription. Thank you. The prescription.
Oh, am I taking this thing?
No. Okay, so this thing right here is an alcohol.
Smartly, are you going to screen share?
Oh, I'm sorry. You're right. I'm not screen sharing. Give me 1 second. Sorry. I forgot to screen share. Thank you for reminding me. All right, better. So this guy right here is an alcohol, and in order to produce a precipitate, we're going to want to be mixing ionic or salt solutions. So I'm just going to instantly get rid of this guy. Okay, it's an alcohol. We want salt solutions to produce a precipitate. Okay, so now we need to look at when people pair up. I guess they're not people, when solutions pair up, what the final outcome is going to be. So I'm going to start over here. Look at, if these guys switch, potassium is with acetate and the other potassium is with permanganate. Now, alkali metals are always soluble. So like these two guys can't switch and produce any sort of precipitate because you'll get alkali metals as products, okay? So what about this guy and this guy? Well, sodium is an alkali metal, so you'd get sodium permanganate and potassium chloride. All alkali metals for products. Alkali metals are always soluble. So what about sodium chloride and this guy? Well, you'd get sodium acetate, alkali metal, and acetate soluble, and you'd get potassium chloride. Potassium ion is always soluble, so that doesn't work. So then you go over here. One of the products would be sodium nitrate, which would be soluble, but the other product is lead 2 chloride. That is not soluble. It's not an alkali metal. It's not a nitrate. So lead 2 chloride would be your ones that precipitate. Whoa, okay. Let's back up. PbCl2. Okay, so it's these two solutions. Solution 1 and solution 2, when combined, would produce a solid precipitate called lead 2 chloride. Any questions on that one? Okay, let's keep going. So the mole, you've actually worked with the mole before, hopefully. The mole is interchanged between mass and molar mass. So if you know mass and you know molar mass, you can get the mole. If you know any two of the three, you can rearrange the equation to get the other one. So if you know mass in moles, you can get molar mass. If you know molar mass in moles, you can get mass. You can just rearrange them. Now, believe it or not, they give you this equation on your equation sheet. So if you look down on the second page, and you look right here, the answer key, or I guess I call this like the legend, this tells you what each variable stands for. So N stands for moles, and M stands for mass, and big M stands for molar mass. So moles is mass over molar mass. Now, you guys actually already knew this, okay? You knew this because you knew how to convert mass and molar mass to get moles. Now, you're not used to seeing it as an equation, but let's say I gave you like 5 grams of sodium chloride. That's mass, right? And I want moles. Well, you'd look up sodium chloride's molar mass on the table, which is 58.44 grams per 1 mole, and you would turn it into moles. So this is mass divided by molar mass, which is exactly what this is showing you right here. So again, if you know any two of the 3 variables, you can solve for the third. Okay. Sorry, I'm trying to get back to my PowerPoint. Okay, so let's keep going. The units for solution, which you did use last year, are called, well, for the sake of this class, we're going to only use molarity. Molarity or molar means moles of solute, so the thing that's being dissolved, it's usually some sort of salt, very often, per liter of solution. Now, the solution is the solute and the solvent combined together. So this solution is solute and solvent combined. Okay, so moles per liter. So if you go on your equation sheet again, I need to move this up here. Sorry. No. Sorry, give me 1 second. I need to move my Zoom toolbar. It's getting in the way of everything. Okay, so if you go to your equation sheet, right below the moles and molarity, so you have the equation for molarity. Molarity equals moles of solute per liter of solution. So in essence, they're telling you molarity equals moles per liter. Okay? So again, this is kind of like the moles equation. If you know molarity and moles, you can find volume. If you know moles and liters, you can find molarity. If you know volume and molarity, you can find moles. So if you know two of the three variables, you're able to rearrange and solve for the third, okay, which is just what this slide is referring to. For aqueous solutions, our solvent is always going to be water. That's what it means to be an aqueous solution. So we're going to do some practice problems with determining concentration. Molarity means concentration. So it says calculate the concentration, which means they want you to calculate the molarity. So this means molarity. They want you to calculate molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So concentration, molarity equals moles per liter of solution. So I did not directly give you moles, but I gave you grams. And since you know the formula of the compound, you can turn grams into moles. So 23.4 grams of sodium sulfate. So what is that guy's molar mass? I have no idea. If you know it, you can shout it out. Otherwise, I'm going to take a second to figure it out. So this all comes from the periodic table. It is 142.04 grams per 1 mole. So 23.4 divided by 142.04 is, I'm going to write out a bunch of numbers. Here's why. I'm not finished. So you don't want to start like rounding yet. Ooh, 23.4 divided by 142.04. 164,777. Does that sound right? Okay. Moles divided by, right? Moles divided by liters. Now, I know I didn't give you liters, but I did give you milliliters. So this is just a metric conversion. There are 1,000 milliliters in a liter. So it's 0.125 liters. So you take and you divide by 0.125. Something's off on this number, and I'm not sure what it is. It doesn't look like my number from the last class, so 1647 divided by 0.125. Oh, I lied. I just put it in my calculator. Excuse me. So you get 1.3179 something something something. Well, this is 3 sig figs and this is 3 sig figs, so your answer is going to be 3 sig figs. The 7 can absolutely round that up. So you get a 1.32 molar solution of sodium sulfate. Do I have any questions about this problem? Okay, so let's keep going. So this problem just asks for a different rearrangement. They want to know the mass of the solute. So that's the solid that's going to get dissolved. And then they want you to make 250 milliliters of a 1.2. Remember, this means per. So this is moles per liter, molarity, sodium carbonate solution. So, okay, well, who's sodium carbonate? Sodium carbonate is Na2CO3. Okay, and they want to know mass. Well, what's mass? Mass is grams. So you go, okay, well, what do I have? So molarity equals moles per liter. So they gave you molarity, that's this guy. They gave you volume. I mean, I know it's not in liters, but you can convert it to liters. So you can get moles. Once you know moles, since we know who the substance is, we can turn moles into grams using molar mass. So rearrange the equation. Molarity times liters is moles. So let's look at the numbers. 1.20 moles per liter times 0.250 liters, right? That's milliliters to liters. And that gives me 0.3 moles. Well, I didn't ask for moles. I asked for mass. So I need to turn the moles into grams. So 0.3 moles of sodium carbonate. And for every 1 mole, now you got to go to the periodic table and find the molar mass of sodium carbonate. And it's 105.99 grams per mole. And you multiply those out. This is a 2-digit number. This is a 3-digit number. So your answer should be 3 digits. So you get 0.3 times 105.99. And it's 31.797. But with 2 sig figs, it would be 32 grams of sodium carbonate. Do you have any questions on this one? Okay, well, let's keep going then. So what happens, so you can do this math, right? The math isn't actually too complicated, but what happens is on an AP test or on my test, someone could ask you, well, what is the point of the math? Like, what are you doing? What does that mean? So they could ask you to describe how to prepare a solution, okay? So, oops, sorry. I'm going to go back. So we said, okay, we need 32 grams of sodium carbonate to make this solution. So how do we do that? Well, here's how you do it. How would you measure out in a lab 32 grams? What piece of lab equipment would you use? Anybody? So you should use like an electronic balance, okay, to mass out 32 grams of sodium carbonate, okay, on electronic balance. We would usually use something like a weigh boat to pour this, this is the salt into, because you don't ever want to pour chemicals directly onto the balance. So you would mass out 32 grams of sodium carbonate on the electronic balance, okay? Now, when we prepare solutions, for the sake of this class, you can prepare them in 2 types of containers, 2 types of laboratory equipment. I know you should know one of them. When we make solutions, they're sometimes called stock solutions, and they're called stock solutions because we know their concentration, and we know it because we're the ones making them. When we prepare solutions, we want to use containers or glassware that has really, really good markings on it. Does anybody want to shout out one piece of glassware that has really good markings on it that we could make a solution in? Anybody? I know you guys are using the chat, but yeah, graduated cylinder. Good. Okay, so a graduated cylinder could be one. Okay, Graduated cylinder. It has lots of markings on it. They're good to make solutions in. Today I'm going to introduce you to one that you might not be as familiar with. It's a volumetric flask. Okay. Now, volumetric flasks are wonderful for making solutions, but you have to have the right size volumetric flask because volumetric flasks only have one mark on them. So like if I want to make this solution, what size volumetric flask do I need? Well, you have to go back and look. It needs to be a 250 milliliter volumetric flask. So I'm going to whip out my 250 milliliter volumetric flask. Volumetric flask. Okay. So then I take the salt, I massed it out, now I have 32 grams of it, okay? I dump it in my flask. So now the salt's kind of just sitting here at the bottom, and this next step is really important. You're going to add enough water to dissolve all of the solute, the sodium carbonate. So you don't fill up to the final mark instantly. You make sure all of this gets dissolved first. Before you can fill up to the final mark. So you add enough water to dissolve all of the solid, and then once the solid is completely dissolved, you can fill up to 250 milliliters with DI or distilled, that's what it means, water, this pure water. And now you have made 250 milliliters of a, let's see, what concentration was that solution? 1.2 molar. So you now have, this is 250 milliliters and it's 1.2 molar sodium carbonate. Do you have any questions about how to prepare a solution? Okay, so let me move this a little bit more. Gosh, I'm having an issue with this toolbar. So the next slide has pretty much what I said, kind of, you could write 32 right here. Sorry, I know it says 31.8, but you would put 32 grams of sodium carbonate, add it to a volumetric flask. You could have just as easily picked a graduated cylinder as long as it was a 250 milliliter graduated cylinder. Dissolve all of the solid with DI, distilled water, and then fill up to the final mark with distilled water. So for right now, what's going to happen is I'm going to give you a simulation of how you would actually prepare a solution in the class from a solid. You're going to have to calculate out how much you need of the solute, and then you're going to kind of prepare it. There are 5 different examples. I want you to try to get through as many as you can. I'm going to give you about 5 to 7 minutes to do this on your own. It's a simulation. It seemed that kids could not access it through my PowerPoint, so I'm going to share, once I find the chat, I'm going to share the link with you in the chat. So here's the link in the chat, and I'm going to kind of mute myself and let you guys go off and try to prepare your solutions, and then I'll stop you. If you don't finish all 5 by the time I stop you, it's not a big deal at all. I just want you to get used to the process, at least virtually for now, of how we would prepare a solution in a lab. So I'll be hanging out here while you guys try to work those out, please. All right, so this next problem is just like the ones we've been doing. It says typical blood serum has a little bit of a concentration of salt in it, sodium chloride. They want to know what volume in milliliters of blood, and then they give you a mass of sodium chloride. So we try to figure out, okay, well, what do we have? So let me type up here. Molarity equals moles per liter. So they gave you molarity, it's right here, and they did not give you moles, but they gave you milligrams, and you can turn milligrams into grams and then grams into moles using molar mass because we know it's sodium chloride. So they also, in a roundabout way, gave you moles, and they're asking for volume. So what volume? in milliliters. So you can solve for liters and then convert to milliliters. Now what's tricky about this is you can't solve for something while it's in the denominator. I don't want you to leave it there. So in order to get it out of the denominator, you have to multiply both sides by liters. So it's liters times molarity equals moles. Now to isolate the liters, you have to divide both sides by molarity. So it comes out to be liters equals moles over molarity. So that's the equation we're going to use. So now we got to do some math. We've got to turn milligrams into grams and then grams into moles, and then we can plug that in, and then we can just plug the 0.14 in for the molar. So 1.0 milligrams of sodium chloride. It is 58.44, oops, sorry, my bad. Metric conversion first. 1,000 milligrams in 1 gram. And then it is 58.44 grams in every 1 mole. So you take and do those numbers. 1 divided by 1,000 divided by 58.44 is, oh, lots of zeros. 0.00001711 moles divided by, the molarity was 0.14 molar, so 0.14. Now, excuse me, I'm going to rewrite molar so you can see the units. Molar stands for moles per liter. So look at your moles cancel and you're left with liters. So you divide by 0.14 and you get 0.00012223. Well, this is 2 sig figs and this is 2 sig figs, so your answer is 2 sig figs. Liters. Remember, because the molarity equation only has liters in it. But they asked for milliliters. So there are 1,000 milliliters in a liter. So you would move the decimal 3 to the right, and you end up with 0.12 milliliters of sodium chloride in that solution. Do you have any questions about that? Okay. All right, so let's move on. So this says calculate ion, and then these brackets mean concentration. Because really when we take these ionic compounds and we dump them in water to make aqueous solutions, they don't stay intact. They literally float around as ions. That's why they're called electrolytes, okay? So really what you're doing when you're taking zinc chloride and making it into a solution, it's no longer zinc chloride. It doesn't stay like this guy. It breaks apart. That's it dissolving or dissociating into its ion counterparts. Okay, so they want to know the number of moles of solely chloride ions in zinc 2 chloride. They gave you molarity, they gave you volume, you can get moles. What's the equation? Molarity equals moles per liter. So you rearrange. Molarity times liters is moles. So the molarity is 1.0 times 10 to the negative 3 moles per liter times 1.75 liters. This cancels. And you end up with, it's 0.00175, I think. So 0.00175 moles of zinc chloride. Now, I didn't ask about zinc chloride. I asked about chloride ions. So you would say for every 1 mole of zinc chloride, for every one of these right here, you produce 2 moles of chloride ions when it breaks apart in solution. So you actually have to take this number and multiply it by 2, and that's how you get 3.5 times 10 to the negative 3rd moles of chloride ions. There's actually more chloride ions in there than there are zinc ions, because when this thing breaks apart, it does this. Zinc 2 plus and then a chloride ion, and then another chloride ion every single time. So there's double the chloride ions present floating around in that solution, and you have to account for it. Do I have any questions about that? Okay, let's keep going. So calculate the ion concentration for these soluble salts down here. Now remember, salts, all of these ionic compounds will dissociate, dissolve, ionize, break apart. Sometimes they even call it dissolution. Again, all of that just means dissolving or breaking apart into ions. So I'm going to do the first one with you, and then I'd like you to see if you can try the next one on your own. So 0.50 molar cobalt 2 nitrate. So you go, okay, cobalt 2 nitrate, cobalt 2 nitrate. So what does this thing break apart to in solution? Well, it breaks apart into cobalt ion and 2 nitrate ions. Does anybody know? You can shout it out if you know, and it's okay if you don't. A lot of kids, I think this is one color, and it's not. Anybody know what color cobalt 2 plus is in solution? Anyone? It's like a pinkish red. And I think that the common thought is that it's blue, right? You always hear like the word cobalt blue. And there is something called a complex ion with cobalt that is blue, but like the cobalt 2 plus ion itself is actually like a pinkish red. It's really, really pretty. Of course, pink, those are my favorite colors, so that's why I probably think it's so pretty. But it does produce a colored solution, kind of like copper 2 plus ions produce a blue solution. So this solution actually in a container looks pink. It's not colorless. So look you have 0.5 molar of the cobalt 2 nitrate. So you can do this conceptually. For every 1 cobalt 2 nitrate, there's 1 cobalt ion. So it's 0.5 molar cobalt ion because they're in the same ratio. But the nitrate ion is double, so it's 1 molar of the nitrate ion. 2 times 0.5. What I just did is, mathematically, I did 0.50 molar of the cobalt 2 nitrate. And then I said, for every 1 of the cobalt 2 nitrate, sorry, I know this is horrible, there are 2 nitrates. And yes, I'm interchanging molarity with moles. You can, for just these type of problems, plug in molarity instead of moles, okay, because they're all on the same size volume. Good. So I'd like you to try the iron 3 perchlorate. I want to know how much of each ion is present when iron 3 perchlorate dissociates in solution. So I'm going to give you a minute. I want you to try it. All right, so iron 3 perchlorate is FeClO4 3, and it breaks apart into iron 3 plus ions in solution and 3 perchlorate ions. So if this is 1 molar, this is a 1-to-1 ratio, so this is also 1 molar. And this is a 1-to-3 ratio, so this would be 3 molar perchlorate ions. That's because for every time it breaks apart or dissolves in solution, it does this. There's an iron ion and 3 of these guys that float around in there. That makes it more concentrated because there's more of them. Any questions? Okay, so on the AP test, they actually have asked this before, where it's a multiple choice question, meaning you should technically be able to do this without a calculator. So solid cobalt 3 nitrate is added to distilled water, so they're making a solution, and they tell you the concentration of the nitrate ion that comes out in solution, and they want to know what the concentration of the cobalt ion is. So all we have to do is break apart our cobalt 3 nitrate, cobalt 3 nitrate, into its respective ions, cobalt 3 plus 3 nitrate ions. Now they gave you the concentration of the nitrate ions, 0.100 molar, and you go, oh, I need to find this guy. That's who they ask about. Well, this is a 3-to-1 ratio, meaning whatever number this number is triple that. So if you can do that math conceptually, in essence, you're going to divide by 3. But I'll show you mathematically what you're doing. You're saying 0.1 molar nitrate ions, and that there's 3 nitrate ions for every 1 cobalt, cobalt ion. So 0.1 divided by 3. You could look at this mathematically if you can't do this in your head, but as 1 divided by 3. 1 divided by 3 is 0.33333, right? But it's not really 1, so you got to move over 1. So it's 0.033. The answer is B. So again, math without a calculator for ion concentration of a solution that breaks apart into more than 1 ion. Do you have any questions about that? Okay, let's keep going. So dilutions are often done when you take 2 solutions and you mix them together, or you take a solution and then you add water to it to dilute it. So you're either throwing 2 different solutions together to increase the total volume, or you're taking a solution and adding water to it and diluting it that way. Either way, if volume increases of a solution, it's always going to become diluted regardless of what you put in it. Okay, so there's 2 important words. I want to know in the wording, it says, what is the total volume if you take 40 milliliters and you dilute it to 100 milliliters? Well, that means you're taking a container, okay, right? And it already has 40 milliliters of stuff in it. And you're just adding until you get to 100. So the final total volume is 100. In essence, you're taking something that's 40 milliliters and you're adding 60 milliliters likely of water until you get to 100, and your 100 is your final volume. So diluted to means this is your final volume. Now this is contrary to being mixed with. So when you take 2 solutions and you mix together, their volumes are additive. So it could be added to, mixed with, combined with. So if you take something that's 40 milliliters and you take and mix it with something that's 60 milliliters, so you take this and then you mix this in here, you now have a total of, 100 milliliters, not 60 milliliters. You now have a total of 140 milliliters of stuff in the container. So the total volume with this wording is going to be 140 milliliters. Questions? Okay, so there is an equation. This one is not on your equation sheet. It's M1V1, M2V2, where if you know 3 of the 4 variables, you can solve for the 4th. So this is a beginning concentration, beginning volume, final concentration, final volume. Okay, so here we go. Let's do an easy dilution problem. It says, what is the new, remember this means concentration, if I give you 50 milliliters, so there's a volume, of 0.24 molar, there's a concentration, hydrochloric acid, and it's mixed with, this is an important word, mixed with 150 milliliters of water. Okay, so they're going to take the acid and they're going to add, there's going to be water with it. So obviously you're diluting the acid. If you add water to something, it becomes more diluted. Think about making like Kool-Aid. If you make Kool-Aid, you pour the sugar in there, right? And then when you pour the sugar in there, it's a certain amount of sweetness, certain concentration, right? Well, if you want it to be less sweet, which would be less concentrated, what do you do to it? You dilute it by adding more water. That would make it less sweet, aka less concentrated. So can someone shout out, will your final molarity be more than or less than 0.24 molar once we add the water? Should our final concentration be more or less after adding water? Less. Thanks, Brian. So less, right? If you add water to a solution, it's going to make it less concentrated. So hopefully our answer comes out to be less than a number than less than 0.24. So here we go. Easy equation. M1V1 M2V2. This is the dilution equation. What is my initial molarity? My initial concentration is 0.24 molar. How much of it do I have? 50 milliliters. What's my new concentration? I don't know. That's what I'm solving for. Now, this is important. What's my final V2 volume? 50, 150, or 200? Yes, it's 200 because you took 50 milliliters of the acid solution and you added 150 milliliters of water, which means you have 200 milliliters of stuff. So the math is very easy. You divide both sides by 200 milliliters. Milliliters cancel and you're left with molarity. And look, this is less concentrated, 0.060 molar. 2 sig figs, 2 sig figs, 3 sig figs. So this is multiplication and division, so we use 2 sig figs. Now, something that I just realized I skipped over. How come in our molarity equation, that's this one, you can only use liters. You cannot use milliliters. You cannot use milliliters in this equation. Never, ever, ever, ever. Why can you use milliliters in this equation? Does anybody know? You can use milliliters or liters. You can use either one. Does anybody know why?
Because it's multiplying and there's milliliters on both sides of the equation.
Perfect. Perfect. So the volumes are on both sides, so the milliliters can be canceled. There's only volume right here in this equation, so there's no way to use milliliters in there because there's no other milliliters to cancel like there is in the M1, V1, M2, V2. Okay, so let's do a little bit harder one. So they're going to take 50 milliliters of aluminum chloride, and they're going to mix it with 150 milliliters of sodium chloride. So they're taking two different solutions and throwing them together. Now they want the concentration of every single ion after you mix. So let's try to draw this out. I have one container that has 50 milliliters of aluminum chloride. And then I have another container that has 150 milliliters of sodium chloride. Okay, they're going to take these two and combine them. So this is going to get dumped in here, and this is going to get dumped in here to make a total solution that has what final volume? Should be 200 milliliters, right? 150 mixed with 50 should be 200 milliliters of aluminum and chloride and sodium and chloride. But they want to know the concentration of each ion after mixing. So here's where this is difficult. Because you have different amounts of each substance you're using, you have to do M1V1, M2V2 twice. You have to do it once for the aluminum chloride, and then you have to do it separately for the sodium chloride. Okay, now there is something that both of these equations will have in common. Which variable will be the same in both equations? The M1, the V1, the M2, or the V2? It will be the same in both equations. Which one is it? It should be V2 because now that they're both in the same container, they should both have the same final volume of 200. Questions so far? So let's do it. What is M1 for aluminum chloride? Let's do aluminum chloride first. It is 0.2 molar. How much of it do I have? I have 50 milliliters. M1V1 equals my new concentration after I mix them out of 200 milliliters because that's my final volume. And you will end up getting 0.050 molar aluminum chloride. Okay, so that's the first one. Now, Let's do the one for sodium chloride. What was sodium chloride's initial concentration? Well, it was 0.1 molar. How much of it did I have? I had 150 milliliters of it. Sorry, I'm kind of running out of room. What's my new concentration? M2, I don't know. What's my new volume? 200, because I mixed them. So you rearrange and you get 0.075 molar sodium chloride. Now, the problem is that it's not really these guys when they're in solution. When they're in solution, they're floating around as aluminum ion and 3 chloride ions. And this guy's floating around as sodium ion and chloride ion. So you've got a bunch of sodiums in here, chlorides in here, aluminum in here, and so forth, okay? This is a Cl, okay? So when I say 0.050 molar aluminum chloride, sure, it's 0.050 molar aluminum because for every 1 aluminum chloride, there's 1 aluminum ion. So 0.050 molar of aluminum ion. But there's triple the chloride ions. So you have to actually take 0.050 and multiply it by 3 if you want to know the concentration of chloride ions in there, which would be 0.15 molar chloride ions coming from the aluminum chloride. Okay, now the sodium, there's 1 sodium and 1 chloride ion. So 0.05 molar sodium ion and 0.075 molar chloride ion. Okay, well, there's 2 sources of chloride ions. So the total concentration would be additive. So the chloride ion from aluminum chloride, so 0.15 molar, plus the chloride ion from sodium chloride, which is 0.075. And that's going to get you this 0.22 molar of chloride ion because there's 2 sources of chloride ions floating around in there. Aluminum is contributing chloride and so is the sodium. How are we doing? That was a little bit harder. Do I have any questions?
If you were to add it, like 0.15 plus 0.075 using sig fig rules, wouldn't it round up? Because it was 0.225.
You'd follow the decimal place though for adding, remember?
Oh.
And then this guy messes you up that this is a 2-digit number. Because you end up with 0.225, you mean for liters? Or, no, oh, I see what you're saying. So that's that even odd rule. If you put 0.23, I'm okay with that.
Okay.
Okay?
Thank you.
Good question. Okay, next. This is another harder one, or medium in the middle of the road. Okay, so I take a 60-gram sample of sodium hydroxide. This is a base, strong base, and I dissolve it. So this is obviously a solid. I dissolve it in 250 milliliters of water. So in essence, this part right here, they've just prepared a solution. Question so far? What can you find out right now in just this first sentence about the solution? What can you find out about the solution?
It's dissolved, so like the numbers aren't like added together.
Right.
They like I think they reach 250. That's what I think. I don't know.
So they will reach 250, but if you take this much sodium hydroxide grams and you have volume, what can you find out about the sodium hydroxide solution that they just made?
The moles?
Molarity, right? You can find out the moles, and then once you know moles, since you have volume, you can find out its concentration. So we need to do that. So 60 grams of NaOH, and its sodium hydroxide is 40 grams per 1 mole. Okay. This ends up being what? 1.5 moles into 0.250 liters, right? Molarity equals moles per liter. 60 divided by, 1.5 divided by 1.5 divided by 0.25. is 6. So this is a 6.0 molar sodium hydroxide solution. So in here, they have 250 milliliters of it, and it's 6 molar NaOH. So they just made their solution right here. The next part says they take a sample. An aliquot means sample. They take a sample out of here, 100 milliliters of it, and they dilute it to 400 milliliters. Well, now that we're doing dilution, that's M1V1, M2V2. So now they've taken a sample of this, specifically 100 milliliters of it. So 100 milliliters of it. They put it in here, and then they dilute to, obviously with water, the 400 milliliter mark. So the rest is water, aka they would have added 300 milliliters of water. If there's 100 milliliters of this guy and the final volume is 400, the rest should have been water. So 300 of this is water. So they want to know the new concentration. Well, what was the original concentration? Well, the original concentration was 6. So 6 molar. How much of it did they use to put in here? 100 milliliters equals M1V1 equals, what's the new concentration? I don't know. What's my final volume? It says diluted to 400. So it's not 500. It's not 400 plus 100. It's 100, and then they filled up to the 400 line. So the final volume is 400. So you divide both sides by 400, and you end up with a 1.5 molar solution. So it was 6 molar, and now in this one, it's 1.5 molar sodium hydroxide. More concentrated, less concentrated. Why? They took this concentrated solution and added a bunch of water to it. So its concentration drops. I see some molarity. Yes, good job. I saw that you guys in the chat. I'm sorry, I'm not keeping up very well with the chat right now. Are there any questions on this one? So then this is a little harder. They prepared a solution, and then they took a small part of the solution to make a new diluted solution. Any questions? Okay, so we have a couple more slides. It's going to be based on this last problem right here for today. So one way we learned how to make solutions was taking a solid or a solute and dissolving in water and preparing it that way. That's one way to make a solution. The other way to make a solution is from another solution, meaning not a solid, something that is a liquid, something that is aqueous, mixing with something else that is aqueous, or mixing it with water. So this type of preparing a solution does not involve solids. It involves something that is already in liquid form. Okay, they often call these, again, stock solutions, which means they're solutions with known concentration. So the math is going to be easy. How you prepare it is going to be a little bit different than how we prepared our solution from a solid. Okay, so it says what volume of 16 molar, okay, 16 molar is like the gnarly concentrated sulfuric acid. It, if it spilled on you, it would burn through your clothes, it would burn through your skin. It is very, 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 very concentrated and very dangerous. We only work with it in a fume hood, okay? So they take 16 molar sulfuric acid, and they want to know how much of it is required to prepare, and now they're going to make this new solution. So the sulfuric acid is already in liquid form. It's a solution. Now they want you to make 1.5 liters of it, but they want its concentration to not be 16 anymore. They want it to be 0.1 molar. So obviously a huge dilution is going to have to go on if you're going from 16 molar to 0.1 molar. So the math isn't very difficult, so let's do it. M1V1, M2V2. My initial concentration is 16 molar. I don't know what my initial volume is. I need to figure out how much of this guy I'm going to use. That's what I'm solving for. I want the new concentration to be 0.1 molar. and I want my volume to end up being 1.5 liters. So you take and you divide both sides by 16 molar, and you end up with 0.0094 liters. So the math is great. Great, we have the math down. Any questions so far? Okay, here's the problem. If I say to describe how you would prepare this, if I handed you a bottle, so I'm going to draw this real quick. Are we good with the math? I'm going to delete it so I can have some room. So if I hand you a bottle of 16 molar sulfuric acid, so here's my, they look like this. They're like these big jugs. They have like a little handle on them. Okay. It's, so this is 16 molar H2SO4 in here. Okay. And I say, hey, go measure out 0.0094 liters. What tool are you going to use? You have two options right now. What's one type of tool in a lab that you could use? Okay, I'll tell you, pipette is one. What's another one? Nobody knows how you measure liquids? What tool in a lab do you use?
A balance cylinder?
No, you do not use a balance for liquids.
Cylinder?
Graduated cylinder, perfect. So like a pipette, oops, or a graduated cylinder. So I take my graduated cylinder and I would dump the acid in here. Now, here's the problem. Does the graduated cylinder measure in liters? It does not. So I would like you to convert this because the tool we actually use measures in milliliters. So when you write this out in words, you want to use a volume that would make sense with the type of lab equipment that we're going to use. So you would put 9.4 milliliters in here. 9.4 milliliters of 16 molar super concentrated H2SO4. Okay? Now, so I measure out the acid. I have the acid now. What is the rest going to be? I have the acid. Here's how much acid. The rest is going to be who? Water. Water. The rest is going to be water. So I'm going to make this in a volumetric flask. You could make this in a graduated cylinder as long as it was this big. So I'm going to make this in this really big volumetric flask that measures 1.5 liters exactly. Now here's where you have to be careful, and this is only for acidic solutions. There is an actual method of how you mix acid and water, and it only goes one way. Does anybody remember, does acid go into water or water go into acid? Because this is important, and this is for acidic solutions only. Acid into water or water into acid? This was on your safety test.
Water into acid?
Thank you for trying. It is actually acid into water. So after you measure out the concentrated acid, you're going to put some water in this flask. Now there is a reason. You go, well, why? Why does there have to be water in here before I dump my acid in here? Well, when you dump the acid in here, it releases a bunch of heat, okay? So the water kind of acts like an insulator so that the glass doesn't break. If the glass breaks, you end up with 16 molar sulfuric acid on you, and that is a big problem. So if you did not have water in here to begin with, and then you dumped the acid in, and then you dumped water on top of it, there'd be no insulator for the acid, and the heat would likely break the glass and would spill the acid everywhere. So you always, before you dump the acid into the water, you want to put a little bit of water, some amount of water, not 1.5 liters, some number less than that of water in there before you go and dump the strong acid, the concentrated acid into it. So you'd measure out 9.4 milliliters of the sulfuric acid with a graduated cylinder, the strong acid. Then you will take this. You will take the 9.4 milliliters and you will dump it in here, this tiny little bit. 9.4 milliliters is not a lot, okay? And you'll mix it, and then it'll mix all in. And then once it's all mixed, you can fill up to 1.5 liters with distilled water. And now you've created a 0.1 molar sulfuric acid solution, and you have 1.5 liters of it. So on my subsequent slides, this was a blank slide for me to draw on, and I ended up just drawing on the other slide. You have kind of the wording of how you would prepare the solution. And again, I highlighted step 2 because you always want to make sure there is water in there before you pour the acid in there. It's kind of like the step when we prepare a solution from a solid, where you always want to dissolve the solid before you fill up to the final volume. So it's that same concept. That step is very, very important. This is where I stopped. So I'm finished for today. You want to make sure you catch up on your homework for the worksheet that you probably couldn't do until now. I'll hang around if you guys have any questions. Other than that, I'm going to set you free, and then I'll see you on Friday.